Welcome to our geochemistry class. In this class, we will learn about the introduction to geochemistry and geochemical classification of elements that is given by Goldsmith. In simplest terms, geochemistry may be defined as the science concerned with the chemistry of Earth as a whole and of its component parts. At one and the same time, it is both more restricted and also more extensive in scope than geology. Geochemistry deals with the distribution of and migration of chemical elements within the earth and in space also together with time. The science of occurrence and distribution of the elements in the universe as a whole is called cosmochemistry. To properly understand the chemistry of the earth, it is important that we know as much as possible about the chemistry and history of the sun and other planetary bodies in the solar system, as well as the chemistry of stars and interplanetary and interstellar space. What is geochemistry? In simple terms, it is the chemistry of the earth. Geochemistry, as the name suggests, is the bridge between geology and chemistry, and thus, in essence, encompasses the study of all chemical aspects of the earth and their interpretation utilizing the principle of chemistry. So, what are the main tasks of the geochemistry? The main task of the geochemistry is to determine the relative and absolute abundance of the elements and the atomic species, those are known as isotopes, in the earth system. And another task of geochemistry is to study the distribution and migration of the individual elements in the various parts of the earth, that is the atmosphere, hydrosphere, crust, etc., and in the minerals and rocks, with the object of discovering principle governing the distribution and migration of those individual elements. So there are various subsets of geochemistry. For example, isotope geochemistry involves the determination of relative and absolute concentration of elements and their isotopes in the earth and on the earth's surface. Examination of distribution and movements of elements in different parts of the crust, mantle, hydrosphere, etc., and in minerals with a goal to determine the underlying system of distribution and movement. Cosmochemistry includes the analysis of distribution of elements and their isotopes in the cosmos. Biogeochemistry is the field of study focusing the effect of life on the chemistry of the earth. Organic geochemistry involves the study of the role of the processes and compounds that are derived from living or once living organisms. We have aqueous geochemistry that studies the role of various elements in water sets including copper, sulfur, mercury, and how element fluxes are exchanged through the atmospheric terrestrial aqueous interactions. Apart from that, we have regional, environmental, and exploration geochemistry that includes application to environmental, hydrological, and mineralogical studies. So now let's learn the scopes of geochemistry. So the modern geochemistry often focuses on determining how elements are distributed between different reservoirs that make up the Earth and the solar system or beyond. However, its ultimate goal is identification and in-depth understanding of the mechanism by which these chemical reservoirs forms and evolve, thus improving our understanding of how the earth works as a geochemical system. Indeed, the flux of chemical species between these reservoirs, both in the past and at present, as well as in the future provides an important constraint for modeling the past and predicting the future. So now we will learn the geochemical classification of elements. So elements are often categorized based on their general geochemical behavior, even though an element's chemical behavior depends strongly on variables such as temperature, pressure, and chemical environment, the latter of which can be dictated as an element balance state and ability to form complexes. This classification broadly follows the Goldsmith's original classification that is done in 1937 by Goldsmith, and this also adds the organophile and fluid mobile elements. Goldsmith in 1937 divided elements into four different parts. Those are lithophile, siderophile, chalcophile, and atomophile elements. So now we will study these elements one by one. So this is the periodic table indicating the Goldsmith's classification of different elements. So atomophiles are represented by yellow colors. These elements are atomophiles. Lithophiles are indicated in red colored boxes, and these elements are lithophile. So they are mainly rock forming elements. Then we have chalcophiles that are mainly associated with sulfide ores or ores. So these elements are chalcophile elements like Cu, Zn, gallium, silver, cadmium, mercury, etc. Then we have another class of elements that are siderophiles. Those are known as iron loving elements, and these are represented by FeCO(Ni)RuRHPD, MoReOsIrPtAu, CpGe, and Sn. And there are some elements which are artificial. So these elements are artificial elements. In the classification of Goldsmith, elements are divided according to how they partitioned between coexisting silicate, liquid, sulfide, metallic liquid, and gaseous phases. So we can see the gaseous phases. The ones which partitioned in the gaseous phases are atomophiles, for example, hydrogen, helium, nitrogen, and noble gases. There are certain elements which have affinity with the silicate melt or silicate liquid. Those are lithophiles. For example, alkalis, alkaline earth elements, halogens, boron, oxygen, aluminum, silicon, titanium, vanadium, chromium, magnesium, some lanthanides, etc. There are elements which shows affinity with sulfide liquids. Those are known as chalcophiles, for example, copper, zinc, gallium, etc. Then there are liquids which shows affinity with the iron. Those are known as siderophiles. These includes iron, cobalt, nickel, etc. So now let's learn these elements one by one. So what are lithophile elements? Lithophile elements are in fact rock loving, and they preferentially partitioned into silicate minerals. These includes cations that commonly form oxides such as calcium, magnesium, manganese, titanium, sodium, potassium, and the rare earth elements, for example, this LaCe, Br, Nd, Sm, Eu, Gd, Tb, Dy, Ho, Er, Tm, Yb, Lu, and there are some actinide series elements are also involved, that is Act, Hpa, and U. So uranium, thorium, silicon, and Fe are also included in its oxidized states in lithophile elements. So in this particular periodic table, lithophile elements are contained in the red boxes. These all elements are lithophile elements. Then we have siderophile elements. The siderophile elements are in fact the iron loving elements, and they are those that are preferentially partitioned into the metallic core, typically in the form of alloys with iron. The elements exhibiting metallic behavior includes noble metals, that is Pt, Pd, Ir, Ru, Rh and Os, as well as nickel, vanadium, cobalt, etc. Some elements in their reduced states are at high enough pressures to impart metallic behavior and can make alloy with the Fe metals. These includes silicon, carbon and some high field strength elements like niobium. Sulfur may dissolve in the core as a sulfide complex, and under these conditions it is also considered as siderophiles. So these elements represents siderophile. I will show it by the pointer. So siderophile are indicated in this color. These elements are siderophiles. There are certain elements which fall in more than one class as well. So mainly these are siderophiles. There are another class of elements that is known as chalcophile elements, and the chalcophile elements are those that commonly form the ore minerals, a type of mainly sulfide minerals. These includes copper, cadmium, molybdenum, mercury, tin, tellurium, arsenic, as well as some noble metals as well. So if we see these colors, this is representing the chalcophile in this periodic table. So we have Cu, Ag, Zn, Cd, Hg, Ga, In, Tl, Pb, As, Sp, Bi, S, Se, Te and Po. These elements are in fact the chalcophile elements. Another class of elements are in fact the atomophile elements. The atomophile elements are those that readily form volatile compounds at relatively low temperatures, that is less than 300 Kelvin, many of which are preferentially concentrated in planetary atmosphere. Atomophiles include the carbon, oxygen, apart from that hydrogen, nitrogen, sulfur, etc. And these also includes the noble gases. So these are main atomophile elements. I have already told that there are elements which are included in more than one classes. For example, if you see the oxygen, it is included in lithophile as well as in atomophiles. Apart from Goldsmith's class, we have some other class of elements. So we have one more class that is known as organophile elements. So organophiles are those that forms or associate with organic compounds, that is hydrocarbon molecules, in biochemical and biogeochemical processes. These includes carbon, hydrogen, nitrogen, sulfur and phosphorus, but also includes various metal organic complexes. Many metals such as uranium, vanadium, gallium, lead, molybdenum can complex with organic molecules, generating organic rich sediments with high metal contents. So here we can see the organophiles that are indicated by black boxes within the periodic table. So these are all which contains the black are in fact the organophile elements. So we can see the better classification scheme in this periodic table, where we have lithophiles which are indicated by green, siderophiles are indicated by the red color, and then we have chalcophile by purple colors, atomophiles by yellow colors and organophiles by black color, and there is another phase of elements that is known as fluid mobile phase elements that are indicated by blue color. Apart from that, there are certain elements like actinide series. So now we can see in this periodic table the elements which are overlapping between two different classes are also indicated. So here we see that these elements are in fact the lithophile elements, but they are also part of fluid mobile elements. Apart from that, there are various elements which are siderophile, but they are in fact part of some fluid mobile and also of chalcophile elements. There are chalcophile elements which are part of fluid mobile phase and also the part of organophiles. So the last phase is fluid mobile elements. The fluid mobile elements are those that readily is dissolved in the fluids, typically water-rich fluids elements with high solubility in the water and tend to be low field strength elements such as alkali and alkali earth groups, which readily form the inner sphere aqueous complex or highly electronegative elements such as halogens. High field strength elements in the absence of complexin tend to be insoluble. Transition metals, that is D block metals, tend to have lower substrate solubilities, but the presence of anions in the elements can become more soluble if complexed with certain halogens or oxyanions. Introduction of carbonate ions into the fluid or silicate melts can also enhance solubilities of certain elements. So here we can see the fluid mobile phase elements that are represented by light blue color. So all the boxes of these periodic table elements, those have this blue box in between. So those all are fluid mobile elements. Goldsmith pointed out that marked correlation between geochemical character and atomic volume as well. If the atomic volume of element is plotted against atomic number, the resulting curve shows maxima and minima. As we can see here in this diagram, shows maxima and minima. The chalcophile elements are those on the sections in which the atomic volume increases with the atomic number. They are followed by atomophile elements, whereas the lithophile elements are near the maxima and on the declining section of the curve, as we can see here in the diagram. If the heat of formation of oxide is greater than that of Fu, the element is lithophile. The difference between the two heats of formation is measure of the intensity of lithophile characters. Similarly, those elements having oxide with the heats of formation lower than Fu are chalcophile or siderophile. Semi-quantitative measurement of lithophile, siderophile or chalcophile character is also provided by the electrode potential. The elements with higher positive potential, that is 1 to 3 volts, such as the alkali and alkaline earth metals, are lithophile. The noble metals with high negative potentials are siderophile elements, falling in the intermediate range and are generally chalcophile. So the highest potential ones are the lithophile and the lowest ones are the siderophile, and those which have the electrode potential in between these two, they fall into the chalcophile category. So now we can summarize that all the elements are mainly classified into 6 different groups and originally 4 different groups by Goldsmith, and those includes the lithophile, siderophile, chalcophile and atomophile. Apart from that, now there are 2 more groups, that is known as organophile and fluid mobile phase. There are some elements which shows affinity for more than one group because the distribution of any element is dependent on some extent to the temperature, pressure and the chemical environment of the system as a whole. For instance, the chromium is a strongly lithophile element in the Earth's crust, but if oxygen is deficient, as in some meteorites, the chromium is now decidedly chalcophile. So we know that there are different elements which are present in more than one groups. The geochemical character of an element is largely governed by the electronic configuration of its atom and hence is closely related to its systematic position in the periodic table, as we can see over here in this diagram. The lithophile elements are those readily forms ions with an outermost 8 electron shell. The chalcophile elements are those of V groups. Those have 18 electrons in the outermost shell, and siderophile elements are those who are the part of group 8, or in fact in the new, that is 18. So they have in fact outermost electrons are mostly incompletely filled. These factors reflected the other properties also. So we can see the classification of elements according to the Goldsmith. So these are the references utilized in the preparation of this class. You can feel to ask the question related to this class. Thank you.